Um, so taking forward from the last class, in the last class, we have done with the regression analysis. So we are going to do the implementation of regression analysis today. Okay, that is a simple linear regression. We are going to implement it. Let me close this. Now let me open the our coding environment. I'm using the collab, guys, so that the code will be directly there with you. Yesterday there was no class, and twentieth. Okay, now let's implement it. First, I will get lab. First, I want to just have a quick recap what we have done it in our last class and what implementation we are going to do it. Here. So we have seen all these things. The majorly, the error matrix, like we have seen the R square and mean squared error and root mean square error, absolute error. And I showed you different types of linear regression, simple linear regression and multilinear regression. So we are going to implement first the simple linear regression, then we will go with the multilinear regression. And okay, simple linear regression means we will have the one independent column and one dependent column one only. Independent column will be single and dependent column will also be single. Now, when it comes to the in a multilinear regression, here in this, we will have multiple independent columns to predict the single dependent. Okay, and okay, this is a parametric algorithm. I'm going to show you how they are generated this M and C. Okay, now let's go forward. See, I identified okay, I identified a data set, D drive. In this, if I go forward in the data sets, yeah, this is weight and height. Okay, this data set, I'm going to upload it first over here so that it is accessible for you. Okay. Now, this is our, now how you will go forward. Now, we know that the usual implementation process will be like, first, we will get the data acquisition. Then next one will be feature selection. And next one will be like NAN detection. And NAN detection. And there is error detection. And what is next? Encoding, if there is any. Then we will do the data separation and data splitting, because this is a regression problem. So no imbalance. So again, model building, model training, model test. Okay. This is the way we are going to go forward. Just a moment. Yeah, this is the steps we are involved in. And this is the one. Now, first I will get our data. Now I apply here, I will put it as simple linear regression. Okay. Now here I will I'm going to get the data. My data is already uploaded over here. Now I'm going to get that data. I'm using the drive so that this will be there connected to the drive. Whenever you want to use it, you can use it over there. So just give me a minute. It is mounting. The drive is mounting. Yeah, it's mounted. I will go to my drive, and here we have KMA classes, and we will go down over here. 7 a.m. and here we have okay, not this one. Here, artificial intelligence, and this is it. I have to get this data. I'll copy the path. I'm getting the data. Now, first, I will import all the required libraries. Import pandas as PD, first one. Import numpy as NP. Next one, import matplotlib dot pyplot as PLT. Import tbon as SNS. Then we are going to import, yeah, that's enough for us, pd.read underscore CSV. And here I will give you, this is a path. And here I will give it as df data set. Now DF data set is this. Now this one is having 3 columns and 1000 rows. How to see that? DF dot shape. Okay. Now here this is 3 columns. Actually, according to our this one, when we are dealing with a simple linear regression over here, this one, it should have only single independent column dealing with single dependent. But in this, we are having 3 means 2 of them are independent columns, 1 is dependent. Okay. Now, first thing is I will drop 1 column, gender column, I will drop it. So I'll put it as feature selection. Okay. Now, sorry. I will put feature selection. That is, we are selecting the important features, deleting the unimportant ones. So in this case, okay, now what we will be doing is df dot head. In this, I will drop this column. How to drop it? df dot drop. Give it over here. Gender access is equals to 1. That's it. Now here, I'll make this one as in place is equals to. Okay, let me do this. Okay, now okay, now here this is not a, this is a permanent change we made it. df is this. Now this is our independent and this is our dependent. Next important step I told you over here is feature. This one is done. Now we are doing NaN detection and error detection. So first we will go with NaN detection. Okay. Now we are going to NaN detection. That is df dot head. df dot is Na dot sum. There are no NaNs. That's good enough. So next one we will go with error detection. Okay, error detection. Now I will go with first I will get my data set and we will use the SNS dot box plot to find the errors in the columns. Which column is having the error? We will find. There are 2 columns. I want to find out, is there any errors in this? Is there any errors in this with the box plot? So I will give it df. Now you can see it. Yeah, height is having some errors. Weight is having 1 error over. Okay. First, let's check it out the height. Whether how many errors, just to see it clearly. SNS dot box plot you are going to give it SNS means C-bond. Okay. Uh, you are going to give it DF square brackets of height. Here there is some errors. Here there are some errors. That is above the upper limit and below the lower. Now, which error detection we have to use it? We will go with, first we will find the distribution and then we will see that. How to find the distribution? PLT.hist DF square brackets. I will give it as height. Okay, let's see this PLT.show. Now, what I'll do it is, I'll give number of bends more. Bends is equals to 30. And R width is equals to 0.90. Okay. Now here, I want to recheck it. Dot skew dot round. Let's see that. It is 0, 0. So that means to say that it is a normally distributed. Normally distributed means we will go with mean standard deviation method. Mean standard deviation method. Okay. First find the mean. DF dot mean. Here I will give it as mean is equals to M. M is equals to this. And DF height okay, S is equals to this. Here what will happen is M S is equal, we are going to find the lower limit is equals to M minus 3 into S. This is our lower limit. There is upper limit M plus 3 into S. Okay. Now, any value less than lower limit is an error. Any value greater than upper limit is an error. So how you will find out? I'm combining both. So any value, that is df of height less than lower limit or square brackets, directly I'm putting it, guys, height greater than upper limit. Okay. Now here, okay. Now I was getting all true and false. If I want to see the values, I'll give it a df square brackets like this. This is the errors. Okay. Now this one, these are the errors. Okay. Now just remember it. This is the errors we are. Now, how many errors are there? Total 1, 2, 3, 4, 5, 6, 7. See, total our shape is equals to df dot shape is 1000 rows are there. Out of 1000, 7 is not even 1%. 10% is 1000, 10,000 row. If you take it 1000 is 10%, right? From 1000, this is not even 100. That is, it is very, very less than small, very small volume of the errors. It is less than 5%, 1%, less than 1%. Okay, it is 0.1%, something like that. So instead of rectifying it, you can directly delete it. How you'll delete it? Get these errors, dot index. These are the index. Copy these indexes. This index is nothing but these index. These index. I will use the drop directly. df square brackets, sorry, df dot drop within the, here I will put it within the square brackets all. No need to give the access as they are rows. When they are rows, there is no need to give the access. Now, once I do this, it is, they are deleted. How you say that they are deleted? Look at the number here. Previously 10,000, now it is 9,993. Okay. Here I'll make it in place is equals to 2. Now you can see the shape permanent is. Now these errors are removed. If you want to check them whether they are removed or not, just copy this and paste it. Previously I was getting 7. Now I should not get anything. See, I didn't get it. That's fine. Now let's go with the weight. Removing of the weight column. What are the errors are there? I'm going to remove with the weight column. Weight column that shows that one error is there. I'll give it as weight column. Okay. Okay. Now, df square brackets weight and here I'll find the distribution of the weight column. How to find out? plt dot haste. I'll give it, this is my weight column. I'll give it bends is equals to 30 and R width is equals to 0.90. And here I will give it as plt dot show. It looks like normally distributed. Let's see if it be. What I'll do it is, I will take this dot skew dot round. This is also 0. Now it is normally. Again, when it is normally distributed, we will go with mean standard deviation method. Okay. Now I'm taking this. Now here, first I will find out the weight. Sorry, mean. I'll put it in M1. M2 is sorry, S2 is equals to dot ST. I got the mean, and this I will give it S1. And this is S1 is the standard. Why I use the M1, S1? Because I already used it over here, M and S. You see this? Here I use the M and S. So now I'm using M1, S1 for weight. So now I will find out the lower is equals to M1 into 3 S, M1 minus 3 into S. This is lower. Upper is equals to M1 plus 3 into S1. So this should be S1. Now lower is equals to this. Upper is equals to this. Now any value less than lower. Let me do this. Lower is 65. Just a minute. I was just verifying the numbers. So here it is. Lower is 65. Upper is this. Now I will find the errors. That is less than lower or bitwise or greater than upper. This you will get it all true and false. Let's see. I will put it on in the original data frame. That is DF square brackets. This is my original. You put on that one over here like this. There is no errors.